In previous versions of Particleworks, when running a transient conjugate heat transfer analysis, we only had the option to define a uniform heat source over an entire body. For a steady-state analysis, we were able to apply a heat transfer coefficient mapping as the cooling boundary condition, but still only a uniform heat source for the heating side of the equation. In version 8, however, we now have the ability to apply a non-uniform boundary condition to both these transient and steady-state simulations. This allows us to get a better prediction of the temperature in our solid and fluid phases by accurately taking into account heat fluxes from specific regions such as the combustion mapping on the upper side of this piston. In order to enable this, you need to select the body you want to apply the boundary condition to, go to Properties and CHT, and here we are able to see all of the options for different boundary conditions that we can apply. So we still have the option for applying a uniform heat source, and this can either be a constant over the entire course of the simulation, or we can apply one that varies with time using the table. We can also apply a convective heat transfer boundary condition. However, this is only for steady-state simulations. Here we have the option of doing a CSV or using the mapping prof bin from a previous simulation. Please bear in mind that this needs to include both the heat transfer coefficient as well as the temperature in the mapping. Finally, we have the non-uniform boundary condition, and this is where we're able to apply either a heat source, a heat flux, or a temperature, and again, this is mapped over a surface and can vary over that surface. We can apply as many boundary conditions as we require, and these will be displayed in Particleworks when you load them into the simulation. The rest of your conjugate heat transfer settings need to be applied exactly the same as you would in previous versions of Particleworks, and just make sure to remember to solve in double precision as we are solving the energy equation. So single precision will not capture the energy transfer between the solid and fluid phases in an accurate manner.